And welcome back to another lecture of Statistics 479 Time Series Analysis. We have finished our notes. Today is the final lecture, the final content-driven lecture, and it's on a special topic. And that topic is the GARCH model, generalized autoregressive model with conditionally heteroskedastic variance or variation. It's going to be a lot of fun, and people in finance love it. So in today's lecture, what we're going to do is we're going to discuss this idea of the GARCH process. It's a process that extends what we've already done for autoregressive and ARMA models, but now we're going to focus on the variance, because the one big assumption that we've made throughout this course is that the variance is never changing. That is the variance of the white noise process underlying our time series. The variance is always going to be the same, or at least it was always the same throughout this entire course, and that's a pretty strong assumption because very often the variance, the volatility, the varying of our time series will change over time. This is most notable in financial time series because it's very common that you'll be watching the price of some stock, some asset, some whatever, and it's going to be fluctuating kind of randomly up and down, not changing too much, but something happens. And now it's going to still fluctuate kind of randomly up and down, but much more drastically. And if there's an increase in the volatility, that's something that we might want to know about if we're trying to do investments. Now, I don't know really anything about investing, but I do know some things about time series. And today we're going to look at the time series models from our course, but considering that the variance may change throughout time. And this is going to be a new interesting topic, something to do a quick little overview before we end our course. So let's get into the notes and see what this is all about. And welcome back to another lecture of Statistics 479 Time Series Analysis. This is our final content-driven lecture. The next one's going to just be a recap of everything we've done. And as with the last lecture, since I've covered all of the main material that I set forth to do in this course, after the end of the spectral methods, we have another bonus lecture here. But this one, I think, will be particularly interesting for all of those out there who are interested in financial modeling, because we're going to be talking about the GARCH model. Okay, so what in the world is that? Well, it's actually the GARCH process, G-A-R-C-H. You can find it on the website Investopedia, a website that I was recently made aware of by one of my students. And they have a nice sort of qualitative definition of it. And they basically say, well, it's an autoregressive model, but what is the CH, right? We know what AR is, it's autoregressive, but CH? CH is conditional heteroskedasticity, and the idea is that we can use such a model to estimate the volatility in financial markets or other things. It doesn't have to just be finance, but it is particularly of interest to financial institutions who are trying to model the volatility of stock prices, asset prices, bonds, investments, whatever else they do. I'm not really a finance person, so I don't strictly know what they do, but my limited understanding of finance is that if you're watching the price of something, it very well may behave like a random walk. In that case, well, there's a 50-50 chance it's going up or going down. There's not too much you can do, but, flip a coin. However, you could try to model the volatility, because it's very common that you might have times where the price, while fluctuating randomly up and down, will fluctuate only a little bit. And then you might reach a point of increased volatility where suddenly the price will jump up and down a lot. So depending on whether or not you like good stable volatility or more, a higher variance in your investments, well, that's up to the people who manage such portfolios, and hedge funds can figure that stuff out. Mathematically, though, what we can do is we can write down an autoregressive process, and we can change one thing. And that one thing is that we can take the variance of the white noise, and we can make it, well, heteroskedastic, which basically means the variance can change. Because this entire course, the entire time I've been talking for the last 23 lectures, we've always had one main assumption, and that's constant variance, or homogeneous variance. Now, this is a standard assumption in so much of statistics. If we do linear regression, homogeneous variance. We do time series, homogeneous variance. I do design of experiments, homogeneous variance. We usually hope this is the case throughout statistics. It often is not the case. And that's why we need more sophisticated models to study this topic. And that's what we're going to talk about today. We're going to look at the GARCH process, which is the generalized, autoregressive, conditionally heteroskedastic process. And it's a pretty good time. Okay, there's a lot that you could study about this. We're not going to go into all the nitty-gritty details, but at least I'll give you an overview of what this is, and we can apply it in R, and I can show you at least how to use one specific R function to fit such models to data, because it can be a little, well, it can be a little complicated, but we'll get all into that. But first, let's write down what this model is in the notes. All right, so the topic of today's lecture is the, as I mentioned, GARCH model, or process, whatever you want to call it, right? And the rough idea is that if we can start with the idea of an AR1. And the AR1 process, which I've written down probably 100 times by now, right, is going to look something like this. And we'd have phi less than 1 in absolute value so that it's a causal linear process, et cetera, et cetera. But the main thing, as I noted in the introduction here, is that this is constant variance sigma squared. Now, in practice, that often doesn't happen. You have variance that's going to be changing as time progresses, right? You can certainly imagine that you would have, in the finance category, you could have moments of high variability in the prices or low variability. But also, for example, in the case of COVID infections, we'll look at that at the end of this lecture today. But the idea there is that there are times when cases are spiking, and day to day, you might have high fluctuations in the number of cases. And then when we come into a lull and there's not as many cases, you might have very low variability in the day-to-day cases. So those are things that we can all try to look at in the data. But roughly, what we want to do is we want to introduce a new variable here. So we'll say introducing RT, and RT is going to be the return, using the financial lingo, the return or growth rate. And the return or the growth rate can be written in two different ways. The first way we can write it is as the change xt minus 1 divided by xt minus 1. In this case, the return is basically saying, well, how much did the, let's say price, because it's the most natural setting for this. If xt is the price of some stock, then we could look at the change in the price from time t minus 1 to time t, and we can normalize that by the price at t minus 1. So it's like saying, if I bought, one stock at price at time t minus 1, then what's the percentage change one time unit later? Whether we're watching this daily or monthly or annually or whatever, and that's going to be the return. Now, there's another way that's sometimes more convenient. Sometimes you'll see it written as, I'll say approximately, the first difference of the log of xt. And these two things are actually almost the same, because for return rates that are close to 0, because if we were to take this equation here and we were to say take a log and add 1 to it, Well, what happens? Well, we'd have the same thing on the right-hand side of the equation, and we get something that looks like this. T minus 1 divided by xt minus 1. And when we, simplify this, we find out that what we have is the log of xt divided by xt minus 1, which is also just the delta or nabla or whatever, the first difference of the log of xt. So that's true. But what do we know about the log of 1 plus r? Well, the log of 1 plus r is going to be approximately equal to r. This is for r close to 0. You can see this by using Taylor's theorem and expanding the logarithm, using Taylor's theorem and basically throwing away all the higher order terms. And this won't work very well if r is large, but typically the settings of interest, we're going to have r is going to be a little bit above or a little bit below 0, a little bit of a positive gain or a negative gain. And in that case, we can use this formulation as the first difference of the log of the original time series process. And this is something that you will see people use in textbooks a lot, sometimes without even explaining it. They'll say, we have a time series X, we're going to take a log, and then we're going to take a first difference. And that's really where this is coming from. Again, when you take a first difference of a log, you're turning that subtraction into a division, basically. So you're kind of looking at a multiplicative change rather than an additive change. But it's just good to be aware of. And oftentimes authors prefer to use this formulation rather than the one with the xt minus 1 divided by xt minus 1. Right, so now that we have that, the question is, how in the world do we model this? So we're actually going to end up modeling this into pieces. So the first thing we're going to discuss is just the arch model. So first, we'll consider the arch 1 model. And the arch 1 model is just the autoregressive model with this conditional heteroskedasticity and a single autoregressive parameter. Again, you can imagine, just like what we've done in this entire course, we could certainly have p parameters for our autoregressive process. In this case, we're going to just start with 1 because, again, it is the simplest setting to get our head around before we make this more complicated. Now, the model is going to look a little bit different than before. So now what we're going to have is we're going to be modeling RT. So we're going to have RT here, and it's going to equal sigma t times, I guess we can use WT for the white noise piece, WT. And then we're going to have sigma t squared. And this is going to be some coefficient, which we're going to write as, I think, alpha, because I believe that's what they use. They use, I think, omega, but we'll use alpha to coincide with, I think, some of the textbooks and not the R package. Alpha 1 or alpha naught and alpha 1 are going to be coefficients. And we're going to have something that's going to look like this. All right, so let's stare at this for a second. What are these things? Well, we're going to have RT is sort of as above. It's the return rate. Sigma t squared is the time varying variance. Or I guess sometimes they might say volatility. But right, it's the variance term, but now the variance term is varying in time. WT here is still going to be IID, white noise. In fact, I think we can claim Gaussian. I believe, I have to double check the R documentation, but I believe the R function that fits this uses a maximum likelihood approach based on the noise being Gaussian. So again, if we have Gaussian noise, we have this setting, we can do maximum likelihood all as well. But we haven't gotten there yet. We're still writing this all down. And then we're going to have two different coefficients here, which is the sort of constant, and this would be the, I'll say AR1, or the arch, well, AR1. And these are the coefficients that we'd be fitting based on the data. And note that here what we have is we have a square. So it's a little bit confusing, but what we're basically saying is the returns, RT, are going to be modeled as, well, some random Gaussian white noise, so just random variable, but multiplied by some variance. So what does this tell us? Well, this tells us a couple things. It says that, well, I guess we need to do some conditioning first, but roughly what is telling this first equation is telling us is that the returns are going to be mean zero, random, normal random variables, but where the variance is going to be changing in time. Well, we're still going to stick with mean zero here. Meanwhile, the variance term, I mean, this is a standard deviation, sigma, but then the squared, the variance term is going to be affected by the return rate. If the return rate gets bigger than the variance at that next time step, at t-1, if the return rate is larger than at time t, the variance will be larger for the next return, and vice versa. If we have a return rate that is basically zero, then the variance will reach its smallest value. And I should point out, just to make it explicit, that note we need alpha 0 and alpha 1 to be greater than, not greater than 1, greater than 0, as sigma squared t has to be positive because it's a variance. So it would be nonsensical to have negative values in there where you could possibly have negative variance. So we do have that restriction on this model that we have to take into account. Otherwise, yeah, we have a model here where we're modeling a transform. Remember, the return rate is a transformed version of our time series xt, and we're modeling it as having a some sort of stochastically varying variance term. All right. Cool. So what can we learn about this? Well, first of all, we might wonder, why was it conditionally heteroskedastic? Like, where's that coming into play here? Well, it turns out that we can try to figure out what the distribution is, so of RT. So if WT is Gaussian and, nope, I don't need an and. If WT is Gaussian, then let's consider the, well, let's consider plugging this one equation into the other equation. So if I go up to my two equations there, what do I have? I have something that looks like RT is equal to sigma t, which in this case is going to be the square root of the second equation, alpha naught plus alpha 1 RT minus 1 squared. And this is all multiplied by WT. So if we consider the fact that WT is just Gaussian white noise, then if we condition on the previous observation, then the point is that this guy under the square root becomes constant, and the distribution we have is going to be normal, mean zero, and the variance is going to be now, I guess, sigma squared. Well, we still need the variance of the white noise process. Sorry, I realize in the formulation, I should say, we can assume, just for, I guess, identifiability purposes, that WT is going to be standard normal. The point being is that if it has a variance that's different from 1, it would be the same as just scaling alpha naught and alpha 1. So we'd have some parameters that would be fighting with each other. So in this case, we just standardize it and say that the white noise is standard normal, and then we try to estimate alpha naught and alpha 1. Because what happens is when I multiply the white noise by the square root of this thing, it multiplies the variance by, well, that thing. So the variance is going to look like this. So it means that the conditional process, that is RT conditioned on the previous observation, is going to be mean 0, and the variance is going to be dependent on that previous observation. Now, what we can do is we can actually square the above and kind of play around with this a bit. So if we square the above equation, what we get, I mean, the one that just fell off the top of the screen, there it is. What we're going to have is an RT squared is equal to sigma t squared WT squared. Now, what is the square of a normal random variable? Well, W standard normal random variable is going to be a chi-squared with 1 degree of freedom. So if we square everything, now we're looking at the variant and the squared return rate, and our WT squared becomes chi-squared. So we're no longer a Gaussian. But if we also write down the equation above that also just fell off the top of the screen, which is this thing, alpha 1 RT minus 1 squared, then we can subtract one of these from the other, and what we end up with is a new equation. So basically we take these, we subtract one from the other, and we end up with something on the left-hand side that's going to look like RT squared minus alpha 1 RT minus 1 squared minus alpha naught. And then on the other side, well, when I subtract this from itself, what we end up with is a sigma t squared. And then we have our white noise term, WT squared minus 1. So WT squared minus 1 is a centered chi-squared 1 random variable. Because the chi-squared with 1 degree of freedom has a mean of 1. If I subtract 1, now it's centered. It has a mean of 0. Otherwise, nothing much has changed there. So what we can do is we can rewrite this entire thing as a time series process that does not have Gaussian noise, but has some sort of centered chi-squared type noise. That is, if I rearrange the terms here a little bit, what we get after rearranging is that RT squared is equal to alpha naught plus alpha 1 RT minus 1 squared plus, we'll say, nu t, where nu t is going to be a new noise term. It's not going to be, again, it's going to be some type of centered scaled chi-squared noise term, but it's still going to be, it's still something we can work with, right? And now, if we ignore the fact that there's this square going around here, I mean, we basically have something that looks like, so we have something that's just an AR1 process. So this is just an AR1 with a mean and non-Gaussian noise. Cool. So what can we do from there? All right, so the next thing we're going to do is try to figure out, well, now that we have a new time series process in terms of RT squared, we might want to know that what is the mean and variance of RT squared, because now we're going to have our new squared returns here, RT, as a time series, as an AR1 process. Now the mean, or the noise, the noise term is going to be a little bit different than what we saw before, but ultimately it looks just like an AR1 process. And we might want to know, well, what's the mean and what's the variance, and what can we learn about this process? So, well, the first thing to note is above that conditionally, what we have is that the expected value of RT given, well, past values, I guess all the way down to R1, say, if we're starting at, I guess we would have we'll mathematically just assume there's an infinite past. I was going to say, technically, if we're defining RT as XT, as the difference but at XT and XT minus 1, or the log, the difference of the log, then we have to figure out what X of 0 is, and that's going to be a pain. So we'll just say infinite past, etc. It ultimately isn't going to matter because this follows the Markov type property where only the previous value is going to matter. So I don't even need any of these ... dots in here. I just need the previous value when I'm conditioning on the past values of the time series here. And we saw above that this is just going to be 0 because all we'll be left with if we condition on this bit is we're going to be left with some white noise term. But in this case, what it's going to be is it's going to be a centered chi-squared, but it's still going to, because it's centered, it's going to be mean 0. So we don't have anything peculiar going on there. More interestingly, though, is what happens when we consider the covariance. So the covariance of our returns time series, our RT, the autocovariance, I should say, the autocovariance of this thing, sorry, comma. Now, this is going to be kind of interesting, right? Because in this case, if we see that this has a mean of 0, then what we can do is we can just say, well, this is the expected value of the product of RT plus H and RT. So how do we go about trying to sort this thing out? Well, we can actually use something called the Tower property of conditional expectation, something that you may have seen in a probability course, but you may not have, something that you would certainly look at in measure theoretic probability, but I'm not expecting that people have seen that yet. But it basically says that you can take the expected value of the same thing, but then conditioning on the past. So in this case, you condition on RT plus H minus 1 all the way into the past. And what you find when you do that is that you can actually take out the RT here because you've conditioned on it. So effectively, with respect to the conditional expectation, it's constant. Yeah, I know conditional expectation is actually quite complicated, more than you'd expect when you first see it. But we're going to kind of skip over some of the details and just kind of note that if I take this guy out of the first conditional expectation, then the second conditional, the inner one is 0, and this entire thing is 0. And that's pretty neat because that means we have an uncorrelated time series. So if the covariance is 0 here, that means that our sequence RT is uncorrelated. It doesn't necessarily mean that the observations are independent of each other. It just means there is no linear relation in the sense of correlation. So it's a key thing to remember. Just because it's uncorrelated does not necessarily imply independence. It's just, well, uncorrelated. All right, so what else can we do with this? Well, we can work our way through and actually go back to sort out the variance as well. So the variance of RT, I should say this is for H, just to be pedantic and precise, H is greater than 0 to make that work. if I want the variance of this returns, well, what I'm going to get is the expected value of RT squared. Now we have RT squared up here. And we can use this to sort out what the mean is, or what the mean of that is, which is the mean of RT squared, which is the variance of RT, right? Because if we go back to that equation above, what we find is that the mean of RT squared is going to be alpha naught plus alpha 1 times the mean of RT minus 1 squared, but by stationarity, these are the same thing, plus that other term. I think I used nu, the Greek letter, but that's going to be mean 0, as noted above, because it's based on a centered chi-squared, so that doesn't do anything. And what we find is that since these two expectations are the same, we end up with something that's going to look like the mean. I'm going to write mu for mean, is going to be what? Alpha divided by 1 minus alpha 1 and naught, to make sure I got that right. So you can find what the mean of the what the mean of the squared returns is, which is the variance of the returns. So here, alpha naught is just going to be the constant value. It's basically, maybe I should try to interpret these things, right? Alpha naught is kind of like the lower bound on the variance. It's the lower bound on the variance because if we scroll way back up here to when I wrote this down, right, when I'm looking at sigma t squared, the smallest it could possibly be is alpha naught because we're enforcing that alpha 1 is positive or non-negative, and RT squared also has to be non-negative. So the variant can be at smallest alpha naught. So it's basically like saying, what's the smallest possible variance I could have in my financial system, Meanwhile, alpha 1 is the, I'll just call it the arch parameter, the arch 1 parameter. And the larger it is, the bigger the variance is, right? For my returns process, my squared returns process, RT. Now, what we note here is that just based on this equation in blue, what we have is that, we know that alpha 1 has to be greater than 0, or greater than or equal to 0. But if it's equal to 0, it's kind of boring. But it has to be greater than, it can't be negative, certainly. And now we know that it has to be less than 1, or else we would have like an infinite variance for our returns process. That's bad. And it certainly can't be greater than 1, or things just get weird. So we see the same type of result that we would have when we were looking at causal linear processes in the form of an AR1 process, that we would need our AR1 coefficient to be less than 1 in magnitude. In this case, we needed less than 1, but we still want it to be positive, or else this doesn't make sense because we're basically modeling a variance term, not a mean term in this setting. Now, what would happen if we wanted to try to compute the variance of R squared? That becomes a little bit more complicated. So what if we want the variance of R squared? Well, that's, like I said, a little bit harder to sort out, but what we can look at is the fourth moment. The first thing we would want to do is note that, maybe I'll get rid of that question mark. The variance of R squared is going to be R squared squared, the fourth moment, minus the square of the second moment of the, because we're basically computing like the variance of a variance. Now, I'm not going to derive this. You can fight your way through it if you really want to. I'm just going to write down the answer for this fourth moment. The reason being is that I want to interpret the formula. So if we fought our way through this calculation, what we should end up with is something that's going to look like 3 times alpha naught squared divided by 1 minus alpha 1 squared. And then there's going to be a second piece, and that second piece is going to be 1 minus alpha 1 squared divided by 1 minus 3 alpha 1 squared, which is kind of a messy formula. But there's a key thing to note here, and that's specifically this denominator, which only works if alpha 1 is still greater than or equal to 0, but less than 1/3. Otherwise, the variance of the squared returns process, I forgot to put a t here, t, would be infinite, or, it would be nonsensical otherwise. So we have even more restrictions on the parameters if we want to consider this squared process. Yeah, and what you would find is that, basically what you would find is that I would say, I'm just going to, skip to the answer, which is based on the fourth moment of RT. We see that it is what they would call in the jargon terms leptokurtic, which is a very obscure, it's just a weird term. It basically means heavy-tailed, heavier than Gaussian tails. So if you look at the errors, for example, you might have your nice normal distribution, and you have something with heavier tails, which are just, sometimes they call them fatter tails or heavy tail distributions. So that's all that you can derive from this and identify that, right? Basically what we have is we have some type of process. It's a time series process, but the tails of the distribution will be a little bit heavier than just a standard homoskedastic Gaussian white noise type of setting. All right, so all of those equations can get a little messy, but let's just summarize what we've seen about the ARCH1 process. So what does the returns process T do? Well, this is basically like an uncorrelated noise process with heavier tails than a Gaussian. So it's kind of neat. It basically means that if we take our time series and we take a log and a first difference of that log, what we get is some kind of uncorrelated noise process, but where the variance can still change, right? This is when 0 less than or equal to alpha 1 not less than or equal to strictly less than 1. Meanwhile, if we look at the squared process, what we find is that this thing is actually an AR1 process, assuming that 0 is less than or equal to alpha 1 is strictly less than 1/3. Otherwise, the variance would be infinite. You can still kind of think about a process like that, but it would be not ideal. I mean, in some sense, you could think of like a random walk as having an infinite variance in the case that you would run it back if you run it infinitely back in time, then it would have like an infinite variance. So it's not, infinite variance doesn't just shut us down completely in this topic. But if you have alpha 1 less than a third, then you have a nice AR1 process that has a finite variance and everything. So that's always good. Right. So I don't really want to talk about, well, how to fit this, but I'm going to just say really quickly how to fit this model. And what we're going to do is use our good friend maximum likelihood estimation, the maximum likelihood estimator. Strictly, I guess in this case, that is, it's conditional. MLE, because what we'll be doing is conditioning on the previous observations, much like I wrote way back up at the top here somewhere, where I said that the conditional distribution of this RT is going to be normal mean zero with some variance depending on whatever the previous RT minus 1 measurement is, or return rate squared. So I don't think there's anything too novel or enlightening about writing down the maximum likelihood equation, so I'm not going to do it. But roughly it's the same thing we always do, which is we write the joint likelihood as a product of conditional likelihoods. We take a log of that. We get a system of equations after taking derivatives with respect to the two things we're trying to fit here, which is alpha naught, again, that baseline variant or constant term, and alpha 1, which is in some sense the autoregressive parameter. It's kind of like how much the variance will change with respect to the return rate from yesterday. But more interestingly is the idea that we can actually combine, well, we can, first of all, we can make this a, well, there's a lot of things we can do, right? We can make this more interesting by adding different types of time series models together. So I'll say thus far, the ARCH model is only for the noise, or the, I guess, stochastic piece. We're not considering the mean, right? We're not looking at trends. We're not even looking at how xt might change like a stochastic process. We're just looking at the variance term sigma t. That is, specifically, we're looking at sigma t, or sigma t squared, and RT, our transformed series. But we might want to know how the time series value itself, xt, let's say the price of some asset is changing. And that's where we can actually start to combine things. So we could have some extensions like an arch with, I guess, covariates or some linear covariate bit. In this case, what we could do is we could have that xt is equal to, I need some notation here. I guess we can do beta dot zt, some other, well, z could be a time series. It could just be some other covariates measured at any time, right? And then we could have a noise process, which I don't think I used epsilon. No, I used WT above. Good, I'm going to use epsilon t. So when you stare at this equation, it looks a lot like linear regression, but I'm not thinking of it as linear regression. I'm thinking of it as a time series, where here we would have some, I'd expand this and get something like beta 1 zt1 plus beta 2 zt2 plus whatever. I don't really want to use p because p is usually my autoregressive. Yeah, p is overused in statistics. Whatever. Basically, we would have, I'll just end it with, fine, we'll just use p because it's always p dimensions. Maybe we'll use d for d dimensions, even though d is usually the order of the integrated part, the differencing. So Man, I am running out. There are just too many different indices in this subject. I cannot keep. We'll just use P and hope that I don't run into a notation conflict later. But the point is that I could have other time series that are driving the mean of the process xt, and then my epsilon here is not really just epsilon IID noise, but it would be some an epsilon here would be some arch process. So this is how you can think about trying to combine these things. What you would do is you could use the arch model to focus in on the noise, and then you might have some type of covariates, for example, driving the trend or the mean of xt, right? This isn't a trend in time. Like, we could have something like that too, right? I could have, alternatively, I could have something like beta naught plus beta 1 t plus some epsilon t, which would be an arch process. These are all different ways of looking at this, right? Here I would have some linear trend, whereas in the first model, I'd be treating it as having some other covariate. So again, maybe X is the price of some stock and Z is the price of some other stock, or maybe it's the price of some in like some, I don't even know what the right word is, resource like oil or something. So as oil changes, the price of, I don't know, Amazon changes because they got to ship stuff, and shipping burns a ton of oil, right? So maybe that's going to happen, right? It's just a hypothetical example, but something you could imagine. Anyway, we don't actually have to stop there, and that's what's really neat, is that we can actually combine our other processes. We can combine our autoregressive process. For example, we could have something like an autoregressive one crossed with an arch one or something, or an arch p or whatever. In that case, we could actually have a process that looks like xt is equal to phi x t minus 1 plus epsilon t, where epsilon t is again going to be my arch process here in each case. So again, you can kind of go down the rabbit hole and start combining these. And this is only using autoregressive pieces. We can actually extend this to use even into a more complicated settings. So yeah, let's talk about a few more extensions. I'm kind of just hitting these fast because I want to highlight what is out there. And then, of course, if you're interested, you can always spend more time fighting your way through all of the equations and whatnot. So far, we've only talked about an arch order 1 process. We can also do an arch order p process, of course. In that case, all we'd really be doing is changing the equation the equation for sigma squared to be sigma squared is equal to alpha naught plus alpha 1 r t minus 1 squared as before. But now we're going to keep going down the little rabbit hole here all the way to alpha p r t minus 1 squared. Not t minus 1, t minus p, of course. So in this case, right, we can basically sigma squared t depends on previous returns. So that would be one way that we can extend this from a depending on the previous time step to depending on the previous p time steps. And once again, yeah, we can fight our way through a bunch of likelihoods. I don't really want to do that because it's annoying and it's so messy. But more interestingly might be something called the GARCH, which is how I started this section by saying there's something called a GARCH process, which is the generalized, G for generalized, autoregressive, conditionally heteroskedastic process. If we look at the GARCH 1-1 process, what we would have is equations. Once again, we would still have this RT is equal to sigma t wt as above. But our sigma squared t equation, remember, we always get two, like a pair of equations. Sigma is driving RT and RT is driving sigma. Where this model affects things is going to be in how we define sigma squared, or how sigma squared at time t is represented. In this case, we would have something that looks like alpha naught plus alpha 1 RT minus 1 squared plus beta 1 sigma squared t minus 1. So now we have our 1 and our 1. I kind of don't like the notation that they use, because I feel like beta should be more like the autoregressive piece, but actually alpha is the autoregressive piece, because if we shove it into the above equation, then it looks more like an autoregressive piece. Whereas if we, again, shove it into the above equation, the beta looks more like a moving average piece. It can be a little confusing based on our previous discussions on the ARIMA process. So try not to get too hung up on the notation, but this would be like a standard notation for a GARCH 1-1 process. I assume people say GARCH, but I've never actually heard anyone say GARCH, so hopefully that doesn't sound stupid. Regardless, yeah, that's okay, so yeah, it's actually probably a good thing to point out why you can think of this as an ARMA 1-1 process. So similar to above, if we were to square this thing and combine the two of them, so if I were to basically square, square, and square, and combine the two, what I end up with is something that's going to look like RT squared is equal to alpha naught plus alpha 1 plus beta 1 R squared t minus 1 plus some noise term nu t minus beta 1 nu t minus 1. So again, skipping some of the steps, but just giving you the impression that what we have is something that's going to be like an AR piece and something that's going to be like an MA piece, which is where the terminology comes from. It's really AR and MA for RT squared, if that kind of makes sense. All right, and that's more or less everything I wanted to say about the GARCH, or the generalized autoregressive conditionally heteroskedastic model. Of course, if you really wanted to, you can extend this to a GARCH PQ. You could also have some type of ARMA, let's say PQ crossed with a GARCH P prime Q prime model. And in this case, what you'd basically have is one process here, which is driving the hetero, get all the vowels in there, skedastic errors. And then this would basically be driving more like the mean of the process. Right, this is affecting the xt, and this is affecting the errors, which I was calling epsilon t above. And it's quite interesting because you could actually use these ARCH or GARCH models to then do everything that we've been doing in time series, but for the variance or the volatility. So if, for example, going back up to this 1-1 equation here, if I had a time series where I was estimating the volatility or the variance sigma, and I had my returns, then I could do a forecasting for what the volatility tomorrow would be. So that's kind of neat, right? If I have a measure of, if I have, let's say, financial time series, and I have measures of that I can compute the volatility, the return rate, then I can start forecasting volatility. And that could be quite useful because, hey, maybe if the volatility goes up, we want to get out of the market because we get scared. I'm not really sure what finance people do exactly, but it seems like a reasonable approach. Things get volatile. You don't know how much you're gonna, the potential for losing a lot increases, of course, the potential for gaining a lot might also increase. So whatever the hedge funds do is kind of opaque to me. But this gives you an idea of what these models will look like. And I think it's a really interesting extension, something that is different than what we've talked about so far in this course. And of course, there's a lot more to look at, but instead of fighting our way through more equations, we're going to jump into RStudio and see what we can talk about with respect to the volatility of the COVID pandemic. And I think that would be a lot of fun. So I'll see you right over there. All right, and we are back in RStudio one more time. And this time what we're going to be looking at is the fGarch library, or package, that is, which is a package that will, as they say, if they're going to hit enter, right, a collection of functions to analyze and model heteroskedastic behavior in financial time series models. But I've never found financial data to be that interesting. So we're going to look at COVID data instead, which is why I loaded in the Alberta COVID cases, the data set that we've been looking at throughout this course, or at least you have in the assignments, from the beginning of the pandemic in February through last summer in 2020. So just staring at the raw time series, what do we see? We see that it does jump up during that first wave, and it does look like there could be an increase in the volatility. Then suddenly we have this period after the first wave where everything's pretty calm. Suddenly it looks like the volatility could have increased here a little bit in the latter half of the summer before the second wave took off in the fall. Here in Alberta, that is. So how do we work with this type of data? Well, if we go back to the documentation, what we can use is the GARCH fit function. So GARCH fit, if I can spell that correctly. Excellent. And it even has a built-in formula for us. So it starts by just fitting a GARCH 1.1 model to our data. So I'm going to leave it like that for now. Let's try the data. But I need to forget that. Oh, wow. That's right. It is actually peculiar. It's one of the first R packages I've ever seen that has some default data set. I'm not actually sure what that data set is, but it just fit a model to it. So we're going to ignore that. Because what I forgot to do is I forgot to transform my data. I don't want this, right, as my input. What I want is the, we'll call it log difference Alberta COVID. So I guess LDABC. And in this case, right, what we can do is we can have a log of this thing, and we're going to take a first difference. And now we can plot this. This would be effectively like the return rate on your COVID investment, I guess. And it looks something like that. And this is actually quite neat to just stare at alone, because right away you see that early on it looks like not even in say during the first wave, but as the first wave was just starting, you see that it seems to fluctuate much more than as we move on. Now, again, strictly based on the theory that we discussed, this should look like some type of uncorrelated process, but it may not, right? If we look at the ACF, we actually do see a little bit of a spike here. Not a big spike, but there is a little bit of a negative spike there. And our PACF, again, we do see a little bit of a negative spike at a lag of 1. So again, it's what kind of model should we try to fit to this? Well, what we're going to do is go back to this, and I'm going to fit the default model. The default model is to not have any type of ARMA piece, but just to use the GARCH model with the parameter or 1.1 setting. So I hit that, and what we get is a whole bunch of crazy output. This function I'll be honest, I've just looked at it for like the first time when I was preparing for this lecture. It has a ton of output, and it's just mind-blowing, the amount of output that it spits out at you. But let's just see, running with all the default parameters, what happens if we look at a summary, because the summary is going to be a little bit nicer to look at than all this stuff. And okay, let's start at the top. So what do we have here? Well, we have, okay, I love the fact they even have a title in here. They talk about the mean and the variance in this case, where our data is going to be modeled as a GARCH 1-1. The conditional distribution is normal. Presumably, you might be able to change that, somewhere in here where they have norm, whatever S norm is, and some other things as well. So there are a lot more dials that you can turn on this function. We're not going to get into all of them, but I will show you at least a couple of the ideas. Now we have coefficients. So what in the world are these coefficients? Because we've got mu, omega, alpha 1, and beta. It's a little confusing when you first stare at this, because mu, I believe, should be an overall mean, but omega is going to correspond, I believe, to alpha naught in our equations from the notebook that we were just in. Remember what we had for the GARCH 1-1 model? We had alpha naught, we had alpha 1, and we had beta 1. So alpha 1 and beta 1 are here. I believe this is alpha naught, even though if I can understand the way that they write this, where they don't give you a ton of documentation on what all of these things mean, but I believe that's what they mean by omega. And then mu would be like a overall mu, I think, of the process x t then. Or it might just be the difference between, okay, because alpha naught is not strictly that's probably what it is. Alpha naught is not the mean, so presumably we can actually recover mu. If I understand this correctly, what we should be able to do is forget, it doesn't really matter. The point is that we fit our parameters. We get our usual type of thing we would see in a regression. We have our standard errors, we have our t values, we have our p values. We find out that we get a little bit of significance for the alpha parameter. We get a pretty strong significance for the beta parameter here. And even more so, we get a whole bunch of crazy tests on the residuals. So when you look at this, you think, okay, what is going on here? Well, I'm not sure, GARCH, I hope it's GARCH, Bara test is a goodness of fit test. Presumably they're doing goodness of fit with a chi-squared statistic. Shapiro-Wilk is a test typically for, I think, normality. And I believe this is based on R for residuals, R squared for squared residuals. And then we've got a whole bunch of different Young box tests and whatever LM arch is. So there's a ton of different hypothesis tests being done here. They're basically, we can hand wave past it and basically say, these are goodness of fit tests, which are saying, how well do the residuals seem to fit kind of IID, whatever distributions? Well, in certain cases, they don't. In certain cases, you do get insignificant test statistics. So when I see this, my first thought is, okay, we probably didn't do a perfect job at modeling our data, because these goodness of fit tests, whatever specific goodness of fit they're testing, are often coming up with significant p-values. Note that we also get an AIC and a BIC and an SIC and a HQIC, because you can never have enough information criteria out there. So you have whichever one is your favorite, you can work with it for model selection. The other thing that's really neat about this package is it has one of the most extensive plotting functions ever. So if I want to plot this model, it's going to say, okay, I'll give you 13 different plots. Which ones do you want? I'm like, wow, that's quite impressive, I have to say. It even has a little menu. So I could plot the original time series, which looks like that. But more interestingly is plot number 3, because plot number 3 is the series with 2 conditional standard deviation superimposed. So you sort of get this idea of the computed standard deviation of the process, right? Sort of how the errors change. And I think that's kind of a really neat plot to look at. You can get other things like ACF and cross correlation, residuals, etc. The QQ plot at the end is quite interesting. It's a QQ plot of the standardized residuals. This is always a good visual tool to use to determine whether or not your residuals look like they have a normal distribution. It doesn't seem so bad, but you do notice that especially in the one side of the tail here, and even in the other tail, it does start to differ from this line, so it's not perfect. So again, when I stare at this, I think to myself, we could probably do a little bit better with the model that we're fitting. So let's try that. Because I didn't actually put any thought into the model I was fitting here. All I did was fit the default model, which was this GARCH 1.1 model. But we could actually add more things in here. Now, the syntax, I don't know if they're going to give me an example of the syntax or if I'm just going to have to write it out myself. Hopefully they give a nice model of the... No, they're not going to do it, are they? All right, fine. Well, we'll just do it ourselves because they seem to only like fitting the GARCH 1.1 model because I guess that's the model of choice. Again, remember, this model is just for the errors. So when we start to see other changes, the fact that we actually see an ACF for our, what did I call that? LDABC. When we see that we have some type of correlation at a lag of 1, that's different than what we should be seeing, right? We should hopefully, if we take the difference of the log of the time series process, ideally what we would see is something uncorrelated, like we talked about in the notes. We said that RT would be an uncorrelated time series with a variance that can vary. But we don't quite see that. So what we should probably try to do is include something else in our model, like an autoregressive or a moving average piece. So why don't we try that and see what happens? Let's get back to the syntax, and we'll see if I can get this right. What we need to do is we need to give it a formula. And the formula, is going to equal. It's kind of a weird notation, but it's going to be tilde, which is kind of like the output, which I'm going to leave as blank, which is just the time series, is going to be in terms of, I'm going to say GARCH 1.1. Let's keep that in there. But I'm also going to include an ARMA 1.0. So now I have an autoregressive piece that's also in there driving, I guess, this process as well as the GARCH model. And I need to get rid of that question mark, and we'll call this MD1, and it's going to give me tons of output and an error. Why is it giving me an error? I think I just tried this like a second ago before doing this lecture. So, okay, so that's the problem. We have some very finicky notation where I have to put the ARMA process first and the GARCH process second, or else it's going to spit an error out at me saying, hey, the mean has to be one of AR, MA, or ARMA, because I guess it's taking the first thing to be the driver of the mean and the second thing to be the driver of the variance here. So again, we get tons of output when we run this, but if we instead just type in summary MD1, we'll get something a little bit nicer to look at. And now we have a new parameter here, an AR1 parameter. So again, we still have the mean of our process. We have now an autoregressive parameter for our process, and that one is getting a fairly significant p-value associated with it. This omega term, which is like the alpha naught term, which is kind of like the mean value for the variance, or the lower bound for the variance term, is not significantly different than 0 in this case. Alpha 1, it's like kind of getting to significant. But again, it's not a strongly significant term, whereas beta is still very strongly significant. Now, more interestingly, if we look at these goodness of fit tests, which are way too many goodness of fit tests, but that's okay. The p-values are starting to look better. Now, some of these are still significant at the 5% level, but before they were absurdly small. So suddenly it looks like, okay, the fit might be a little bit better. And more so, the AIC here is smaller. Now, let's see if it'll just give me, it's not going to give me the answer, is it? All right, well, I do have AIC here, which is this 0.684. And if we tediously scroll up until we find the previous model that I fit without the autoregressive piece, we have an AIC of 0.83, and same BIC is 9.9, whereas now the BIC is, if I can get to the bottom, is 0.76. So we do see a decrease in some of the information criteria, indicating that this second model looks better. I also love the fact that they even save my name here as Adam K for who ran this and what time I did this. So I guess you can see exactly when I'm recording my lecture, a little bit of a look behind the camera, I guess, to see when this is actually being recorded. It's quite hilarious. I've never seen an R package actually record the user and timestamp when this was computed. I'm not sure why, but it's kind of neat. Anyway, let's go back and look at some of those plots. Because if we go back now, we can look at this plot 3, which I think is quite neat, which again looks at the volatility here. It models this, and we have our standard deviations here, 2 standard deviations of where we think this variance is. Because remember, what we're doing is, apart from that autoregressive piece that I put into this version of the model, what we have is we have a time series that we're thinking of as more of some type of uncorrelated noise process, but where the variance is changing, and the gray lines are trying to look at how wide the variance is as we move through time. We can also look at that QQ plot again, and it looks a little bit better. Typically, when you're looking at a QQ plot, you don't really care about what's happening in the far tails. You just want to look at the bulk of the data and say, okay, most of the residuals are more or less following the normal distribution, with a couple of crazy outliers, as you often see in the tails. Otherwise, there's a whole bunch of other plots you could do. You could look at the ACF of the standardized residuals. That's kind of nice because it says, oh, look, the residuals are looking like they're uncorrelated. That's always a good sign. You can do the same thing for the squared residuals if you really want to. They seem to have something else possibly going on here. So again, like often in time series, you could spend a lot of time trying to fit models to your data. Maybe we'll fit one more just because why not? We're still here. Let's see if we fit an, oh man, I hate all that output. Maybe if we fit, in this case, an ARMA 1-1 along with a, oh, that's quite interesting. So we have an ARMA 1-1 and a GARCH 1-1. And what we see is that the AR alpha piece is now looking not significant. The AR1 piece for the actual mean is looking not significant, but both the MA and the beta terms are looking quite significant. In this case, the AIC and the BIC have decreased ever so slightly, but it hints at maybe what we should be doing is removing the AR and the AR pieces and just fitting some MA pieces. And it gets mad at me for some reason. Order of P must be greater than 0. Okay, yeah, so it doesn't like that. All right, but it's okay with that. So what if we just fit an MA1 for the mean piece, and then we look at the summary of this thing again, and now we get an even smaller AIC and BIC, again, marginally smaller, but still looking better. And at least most of these goodness of fit tests are giving us statistics that are not strongly significant, except for maybe this first one, indicating that we probably have a pretty good fit for our model here in terms of one MA piece driving the mean of the process and a significant beta term here driving the heteroskedasticity or the volatility of the process. Right, so that is more or less everything I wanted to say about this type of model. It's a really neat tool. It seems to be super popular for people who do finance. I don't do finance really, so I'm kind of experiencing this for the first time, but I think that there's a lot of power in here you can see. And the other thing that I didn't mention was that if we go back to the documentation, you can make these models even more complicated, because we included just sort of a mean, but you can also include a skewness term. There's a shape parameter you can include, which is most likely, I'm guessing, a shape parameter for the distribution. I haven't actually investigated what that is. Right, you can change the conditional distribution. There's like these skewness and shape parameters, and there's so many other little knobs that you can turn here to try to fit this type of model to your data. So you can get some very complicated models fit to your data using this function, and it's quite neat. So I'd encourage you to go out and try it yourself, especially because I know a lot of you in your projects for this course were looking at financial data, and we didn't talk about this, so I wouldn't have expected you to use it. But if you're keen, I would definitely, if it were me, I would go back and probably brush off the data set you were looking at and see if there's any type of heteroskedasticity to the variance of the process, because it is something that is quite common, actually. I mean, we saw it here with the COVID data, and it's obviously really popular for financial data, but probably shows up in other areas as well. All right, with that, we have finished the course content that I had outlined. In fact, we finished more than the course content with these extra 2 bonus lectures here, thanks to the speed at which I seem to be lecturing now that everything is edited down on video to a more or less good extent. We will have one more lecture. It's going to be a recap of everything we've done, just to try to summarize where we started, where we went, or where we traveled, and where we ended up here at the end of this course. So thank you as always for watching, and I will see you in the final recap lecture next time.